Hi, my name is Mike Beattie. I'm the CEO of Mediamano, and this is a presentation about deep listening, an advanced system for turning audio into text. What the system essentially does is take audio, which could be in the form of a file or in the form of a stream of audio, and turn that into text. The stream of audio could actually be a stream of audio embedded within a video signal. We can extract the audio and turn that into text. When the audio comes in as a single file, we turn that into a single file with text inside it. When the audio comes in a stream, we provide a continuous output of text, such as closed captions or subtitles. So as I said, it allows speech to be converted into text, which is transcribing. It can work with files or real-time signals. It's very happy to be extracting audio from a video signal, and it uses some extremely advanced tools to take the audio and turn them into text. We'll talk about that in a few moments. It can interface into any system that you have in place already. It can work in multiple languages, and the text that is produced is automatically indexed to be searched later on. Here we have a small graphic describing how it could work in a video environment. On the left we have a MAM system, which is a kind of cataloging system, and in comes a video with President Obama giving a speech. From there we're able to extract the audio by taking a proxy of the video. The proxy is a kind of version with a smaller bit rate or smaller size, which occupies a lot less space, and we can take a proxy of that video and we can extract from it the audio. That's something that we do within our workflow engine. Once that's done, we take the audio and we put it into our GPU. The GPU, which is a system you can see on the right, is a graphics processor, which is a kind of very advanced system, an extremely fast system that can be added to a standard computer system or server to be able to do very, very high speed computing. That GPU, when it receives the audio file, turns it into text in what's faster than real time. So in other words, a 1 minute clip is converted into text in less than a minute. So here we see the GPU working. It's obviously a graphic, doesn't really have cogs inside it. And what it's doing is it's analysing the text of the speech that President Obama has given, and it's turned it into text, as you can see. We take that text and then we put it back, in this case, into the MAM system, so that the catalogue of video that they have now comes accompanied with the text, the transcription of the speech that he's given. And that of course allows us, because it's automatically indexed and added to the search index, it means that if anybody looks for the text in a search system and includes a text that was said by President Obama, it will be able to locate that video because it will recognize the text that was the transcription of what he said. So here's some examples of audio signals. They can come in via IP, that is, if you've got some kind of IP system like an IP streaming protocol or something similar, we could be receiving audio from there. We can receive it also from SDI, which is baseband, so we could be receiving a signal from a camera or from a satellite or some other signal that comes in physically on an SDI port. Of course, we could also be receiving that signal from HDMI, so if there was, again, a camera or any kind of device whose output was HDMI, we can plug that into the system and extract the audio from it. And of course our final one is RCA, which doesn't necessarily have to be RCA connectors, of course. What we're trying to say with this is it can be coming in just as an audio signal, so that could be the output of any kind of device that has an audio output, and we can plug it into the system. And once that's done, we turn the output into the text file. In the case of a real-time signal, of course, it's a type of closed caption. So what can be done with the text? Well, once the text is produced, it can be analysed in real time to look for triggers or keywords or groups of phrases, any kind of profiling that you want to add. You can look for those profiles, and when somebody says a series of words that are of interest to you, the system can trigger the fact that this is coming in from whichever source or that it was said on whichever file it was looked at. It's referenced and stored and indexed for later searching, which means that if you want to, you can make it so that as the text is coming in, not only do we search it, but we also store it away in an indexed form so that you can look it up in a search later on. It can be conformed for closed captioning and subtitles, which means that it can make sure that any words that are not acceptable to be included in a closed caption can be removed. Also, what we can do is we can take the transcription of the video and we can put it inside Adobe Premiere so that it can be edited. So if you have a program, for example, our system can analyze the program. It can suggest the subtitles that you're going to use based on what the people said. And then via Premiere, you're able to go through and change any subtitles that you want to change. There are different approaches to doing this. The state of the art for most companies that are involved in doing audio to text go through the top system here. It does frequency transformation, turns that into something that can go through an acoustic model. The acoustic model takes out of the audio a series of sounds, and they're put into a language model. The language model looks at the sounds, looks at what words probably are being said, and produces some suggested text. Using these systems, you can usually get to about the high 70s, early 80s in terms of percentage of correct words from the text. Okay. Now the second part is some research that's been done in Google, which is using very deep neural networks, machine learning and artificial intelligence, to simply listen to groups of texts and then, just like the brain does, turn those groups of texts into text. And there's another project, apparently, within Google, which is slightly different because it uses some of the aspects of the original state-of-the-art model plus a combination of more modern tools. So it does the frequency transformation. Then it puts it into a deep neural network, which is the part that takes out the pronunciations. And that goes into a language model. This is something that we've actually adopted in Mediamano because we found it can give us extraordinarily good results. But the part that's really good and we're very proud of is that when we take the output from the language model, it gives us a string of words that might not actually be correct. So we put that into our semantic search engine, which is called Happening. And the semantic search engine looks for existence of other articles that have used those words before. If it finds them, then it says, yeah, these words are probably right. But if it doesn't find them, it says, you know, there's probably a word that's wrong here because we're not getting the kind of match we would expect to get. And Happening is already trained with the types of text that appear in this context. So let me give you an example. You could put the audio in that talks about Secretary of State John Kerry, and when that goes into an audio to text engine, it's extremely likely that it'll pick it up as Secretary of State John Kerry, because Kerry is not a commonly used word, but carry is a commonly used word. So the language model, which really should have between 200 and 300,000 words within it, because if you give it too many words, it starts to come out with some really strange results. The language model should have around between 200 and 300,000 words, and it's likely that Kerry will not be included. So the text that comes out is put into Happening, the semantic search engine that's GPU based, and in an extremely short space of time, it checks that text against all of the text that it has inside it, which can be literally up to 32 million documents. And it will do that in approximately 20 milliseconds. And it will tell you which of the documents that are closest to what you've asked it to look for. When it does this, it comes out with a series of documents that say, you know, Secretary of State John Kerry doesn't seem to appear anywhere. So what we do is we say, okay, let's change the language model and let's try a slightly different approach. We put the text in again and say, what about Secretary of State John? And that gives us a higher score because it's seen that more frequently. And we say, okay, well, Secretary of State John is probably pretty close. So what could the next word be? Because it doesn't seem to be carry. So it says, what have you got in your texts, in your documents, that says Secretary of State John and then has a different word at the end of it? And happening gives you that result. And then what we do is we say, oh look, it keeps saying Kerry after Secretary of State John. What does Kerry look like phonetically? And it says, okay, and what was the word that we thought it was going to be? The answer is carry. Are Kerry and carry phonetically similar? The answer, of course, is yes. So then the system says, you know, it's probably going to be Secretary of State John Kerry, not carry. And that's how it works. So what's happening in the world with audio to text? Well, this efficient language model, as we said, has about 200,000 words. Once you give it more than 200,000 words, it starts to make some silly mistakes. So when we build our dictionary, it comes into about 1.5 million words in English. So because our language model has around 200,000 words, technically there are 1.3 million words that it doesn't include. And as we said before, in order to do this, there are different ways to approach it. The Google A method, which was the one that just puts everything into the big neural network, and the Google B method, which tries to iteratively improve its language model, is the one that, according to our own investigations, yields much, much better results. So how does it fit in? This golden globe is what we use as an example of a document that we analyze within Happening. So the globe comes in, which is actually just a document. It's analysed by our system, and the words that are contained within it are given their semantic context. And the document is then mapped within the whole of the memory of the system. So basically speaking, once the document has gone inside, it's automatically in real time included in our search engine and will be picked up. Now in this case we're talking about emissions in cars in this document, and you can see on the left hand side that we have different types of cars and they're kind of semantically similar, and the system picks that up. And on the right hand side we're talking about things to do with emissions and fumes and so on and so forth. I want you please to just look at between fumes and pollution on the right hand side. The word NOx, which is used to describe nitrogen oxide, I believe nitrogen oxide fumes that come out of cars, which are the ones that cause the trouble. Of course, in most systems, NOx as such, when they hear it described by somebody, when they hear somebody pronounce the word NOx, they're going to put K-N-O-C-K-S in because that's how you spell NOx. In this case, we have a different interpretation for NOx, which is the emissions context of NOx. So this is a very typical problem that you come across. And some people will say that the right way to do it is to just keep adding lots of extra words, but of course it misses the contextual part, and that's why it's so important for us to do the language model switch through Happening, because it enables us to get much closer to the context of what's being talked about there. So let's have another example of this. Our audio's come into the language model, and what it's given us after being analysed is Prime Minister Rajoy of Spain. Now, currently, our sitting Prime Minister in Spain is a guy called Mariano Rajoy, which of course has a Spanish pronunciation, but the system would not pick up Rajoy. It's just not part of the 200,000 core words, so it would probably come up with Rajoy. So then we have a look and say, okay, has anybody ever said Prime Minister Rajoy of Spain? And we do the semantic search, and of course, not surprisingly, we don't find it. What we find is Prime Minister Mariano Rajoy of Spain, for example, or you would see another document that said the Spanish Prime Minister, Mr. Rajoy, and then it would say, look, when they talk about Prime Minister in Spain, they talk about Rajoy or Mariano Rajoy, and that's different from what the system originally picked up. So what we do is we say, okay, let's try including that in the language model, and let's have another go. Let's go around again. We'll have another go at analysing that phrase and see if we get a better score from it. So we change it change the language model, and then we rerun that phrase through the language model. And the second time around, of course, it recognizes that it's not raw joy, it's actually rahoy. So we've made a couple of references to this, the same as the case with Knox and Knox, by having a base of documents that are based on what's actually been written down and said in the past. We're able to provide the contextual analysis of the phrase and correct common mistakes that are made by systems such as this when they come up with words that look absolutely ridiculous and sometimes cause absolute hilarity I should say, because they just look absolutely stupid and comical in the context that they're given. So the beauty of continually refining this language model is that you avoid those embarrassing and silly mistakes. So what sort of results does our system give? These are some real-time, real-world tests that we did from 4 different Obama speeches that were provided to us from a news organization. We ran them through the system using just the standard language model and looked at the percentage of words that it got correct. As you can see in this first column, it was very good. Some of the results are very good indeed. 90, 93, 90, 92. Those are great results for a voice-to-text engine in itself. But when you add the semantic search and the iterative improvement within the language model, then the results really leap up. 96% accuracy, 93%, 94%. These are absolutely astonishing results for a voice-to-text engine. Now, I need to point out, and it's important to do so, that this is an Obama speech that was made in very controlled circumstances, so there's no background noise. He does a great job in pronouncing his words correctly. He doesn't swallow syllables or anything like that. So his is a very pure and excellent example to run on. Even so, to be able to get to 96 and 94% is absolutely astonishingly good. And the second part, of course, which is so important, is as the machine is doing this, automatically what it converts into text is included in the indexed search. So even though you might have literally 30 million documents, if you put a piece of audio into the system and it changes that audio into text, the text it produces is automatically in real time added to the index. So if 1 second later, after having run the audio to text, if 1 second later somebody searches for some words and those words are included, it will come up in the list. And if it was the most accurate, the closest to the search terms, it will come up as number 1 in the list. So even the search capability of this, that in real time is giving you access to all of the information that's coming into the system, plus all of the information that's been in the system in the past. It's absolutely astonishing to see it in practice. It's an incredibly efficient system, and only made possible by the fact that we have a group of people who do GPU computing and are able to program these very, very high performance graphics cards and do the searching within the RAM of the graphics card, which is an exceptionally fast piece of hardware. So that's the end of the presentation. As I said, the product is called Deep Listening. It's based on a very, very advanced audio to text engine. And if you want to get in touch with me to talk about where it might be of use to you, here are my contact details. I'd be delighted to chat it through with you. Thanks very much indeed.